Alright, so welcome again, guys. We're continuing our journey, organic chemistry journey, that is, naming these things. We've finished naming our organic species. The only one that we haven't looked at really as yet are esters, but we're gonna just jump into this thing called isomers. Alright, now I like to simplify things. I just like when people understand where things come from. Now, before we even begin too much, we're gonna just break down this word for you. Iso actually means same. So iso means same. And I say mer means unit. Okay? I don't believe you will see that in any textbook or anything of that nature, but I'm saying it. So iso means same for sure. But I don't think mer means unit, but I say same unit. So when we talk about isomers, what are we talking about? What is same? What is similar in these things? Well, these things have the same molecular formula, right? Same molecular formula, but then guess what? They have different structural formula. Okay, so they have the same molecular formula, but they have different structural formula. So we call them isomers, and the occurrence of isomers is called isomerism. All right, so that's it pretty much. They have the same molecular formula, but different structural formula. Now, for you beginning chemistry, when you're just beginning your chemistry, what you're going to find is that your isomers are either going to be what we say branched isomers. Okay, some may be functional group isomers, and you may have positional isomers. So you have the positional, and then you may have your geometric isomers. Okay, that means it has to do some shape thing. So geometric isomers. All right, so you have your branched, your functional group, your positional, and your geometric. So the branched isomers, now we want to look at that, and I'm going to be using the alkenes to show you the branched isomers. So let's write a molecular formula, C4H10. How do I know this is an alkane? All right, the number of hydrogens is 2 times the number of carbons plus 2. The number of carbons is 4. 2 times 4 is 8, plus 2 is 10. The general formula of alkanes, CnH2n plus 2. So this is an alkane. This is a 4-carbon alkane, which means that it is butane. So I could actually draw the structure of butane to represent this over here. So here's my butane. All right. We know it's a bother when we have to put in our hydrogens, but I'll put it in here. Okay, so here is our butane. Now we want to make sure that it fits the molecular formula C4H10. So we're going to count the number of carbons. 1, 2, 3, 4. Let's count the number of hydrogens now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10. C4H10. It matches the formula, the molecular formula, and of course this is butane. All right, now but then I could actually do this. I could actually draw another structure. Boom, boom, boom. Yes, I'm now drawing another structure, and I'm gonna check now to see if this structure, this second species that I've drawn, I'm just going to just put a line of demarcation here. There it is over on the left side of the line, right? What's the molecular formula of this species? Let's check. 1, 2, 3, 4. So 4 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So both these two species have the same molecular formula, but do they look the same? Well, no, they don't. They don't look the same. So let us provide a name for this species. The number of carbons in the longest carbon chain is 3, so this species is actually methylpropane. So it's methylpropane, right? So on the right you have butane, on the left you have methylpropane. But how did I get these two species here? Both of them have the same molecular formula but different structures. So they are isomers of each other. But what I really did was, all I did was just branched the butane. So here's what you can do. If you're given an alkane or an alkene to branch to draw isomeric forms for it, and you need to draw it in branches, you have to draw branched forms of the species. So here you have 1, 2, 3, 4 carbons. Now what I did really was I cut off, or I snipped one of the carbons off the chain like that, and I took this CH3 over here and I put it in the middle of the chain. That's all I did. I simply cut it off and put it in the middle of the chain, and when I did that, I got that there, and I replaced it over there with the hydrogen. And that's pretty much what I did. Now after I did that, I then would have to name the species. So I've made it into a branched species. This is straight, this is branched. So that's how you do your branched isomer. I can show you using the skeletal formula. So watch this now. This time I'm going to use a 5 carbon alkane. 1, 2, 3, 4, 5. Okay, so this here would be pentane because this is straight. And then what I could do to get another isomer is draw 4 carbon alkane. And this, which I cut off of it, because as you can see this is no longer there, I put it here. There you go. Okay, and I name this species. This is actually going to be 2-methyl butane. Okay, and then what I could do is I draw another 4 carbon alkane, and this here I'm going to move it over there. Okay, there you go. Now guess what? When I do that, this species is still going to be 2-methyl butane. So these two species are the same. All right, so now let's look at our functional group isomers. Remember, these things have the same molecular formula, but something is different. In this case, the functional group is different. So let's look at an example. C2H6O. Now just looking at that, you can't really say what it is exactly. It could be a number of things. It could be an ether, it could be an alcohol. It's definitely not an alkene or an alkene, right? And it's definitely not an acid, because acids contain at least 2 oxygens. So it must be one of those things. So I'm going to now draw a structure to represent this C2H6O. So I could actually draw an alcohol, a 2-carbon alcohol, like this. There you go. Right? So that's an alcohol. But then, because it's functional group, so that's the alcohol, you have 2 different functional groups. I could drop something in there and put C there, hydrogens. There you go. This over here is an ether. This is dimethyl ether. Okay, and this right here is ethanol. Okay, let's check to make sure we have 2 carbons and 6 hydrogens, 1 oxygen. So you see over here, 2 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6 hydrogens. So that's fine. Let's check this one. 2 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6. So both of these 2 things have the same molecular formula, but their structure is different. They have different functional groups. And because they have the same molecular formula, we call them isomers. All right, so in this one now, we're going to look at the positional isomers. So remember, isomers have the same molecular formula. I can't say that enough. So they have the same molecular formula. With this now, the position of the functional group changes, and I'm just going to show you that now. So I'm going to use the skeletal formula. Here we have pentene. 1, 2, 3, 4, 5. So there you have pentene. Okay, now with positional isomers, all you're going to be doing is changing the position of the functional group. The functional group of an alkene is the double bond. So all I'm going to do is change the position. Currently it's between 1 and 2. So now I'm just going to move it. And you will see there, I put it over here. I just moved it. These two species have the same molecular formula, C5H10. Okay? But the position of the functional group is different. So we call this 1-pentene. And we call this 2-pentene. Right? The position of the double bond has changed. They have the same molecular formula, so they're isomers of each other. We could look at an alcohol example. Here's a 5-carbon alcohol again. There you go. So this is an alcohol. Okay, it's currently at position 1. I could then draw another alcohol and put it right there in the middle. You see? So this, you're not seeing that. Now you're seeing it. So this there is your position on. I've changed the position of the OH from position 1 to position 3. This is 1-pentanol, this is 3-pentanol. And I could have put it right here on 2 as well to make 2-pentanol. So that's your positional isomers. So you have branched isomers, you have functional group isomers, you have positional isomers. Now we're going to look at the geometric isomers. Alright, so we know at the geometric isomers. So now let me say clearly that these things can get very complex. And as a result of that, we're only looking at a specific type of geometric isomers at the beginning of your organic chemistry life, your CSEC life or your GCSE life, right? So these isomers that we're going to look at, they have to do with alkenes, really. Alkenes, okay? And we call them cis-trans isomers. And of course, you know, geometric has to do with the position in space or the shape of the species, right? So the position in space, all right? So these isomers are cis-trans isomers. In a minute, I'm just going to show you what I mean by that. Now, if you have two similar groups on adjacent carbons of a double bond, so there you have a carbon-carbon double bond, and you have chlorine here and chlorine there, and let's just put a hydrogen there and a hydrogen there. You have similar or the same groups actually on adjacent carbons, carbons beside each other of a double bond. Okay, so I have a double bond beside each other, of course, and attached to each carbon is the same group, chlorine, chlorine. And let's just focus on the chlorine because hydrogen is pretty common. Okay, so these two groups are the same. Now, because of the nature of the double bond, it is rigid. In other words, it does not move. It is not mobile. Not that it moves from place to place, but it doesn't twist and turn as a single bond would. It's stuck in the position that it's in. Because of that, these two groups can be oriented to each other in specific ways. In other words, they can be beside each other or they can be diagonal to each other, okay, in space. All right, this might sound a little bit complex, but in a while you're going to see what I mean. All right, so I'm still going to use that same example. So now, if the two chlorine groups are on the same side, this is how we determine the side, that way. So this is one side, this is the other side. Now, these two chlorines are on the same side. Now, because they're on the same side, we call this cis. Okay, cis. We haven't named it as yet, but they're cis to each other. So we would say that the two chlorines are cis to each other. All right. Then now, because you could get another orientation of this molecule, you could have a case where you have C double bond C, H, H, Cl, Cl. Now, in this case, what you recognize is that the two chlorines are no longer on the same side. They're actually now diagonal to each other. See? They're diagonal to each other. Now, because they are diagonal to each other, we say that they are trans to each other. They're trans to each other. Okay? And then, when you determine their orientation to each other, you can name the species. Okay? So, in this first example, where they are cis to each other, let's go back up there now. So, these two chlorines are cis to each other. Okay? We can now name the species. This is actually 1,2-dichloroethene. Okay? 1,2-dichloroethene. So I'm going to write the name over here. 1,2-dichloroethene. ethene, and of course the ethene should be attached. This is also 1,2-dichloroethene, 1,2-dichloroethene. Okay, both of them are 1,2-dichloroethene, but here's the situation. In this case, the two chlorines are cis to each other, so we say that this is cis 1,2-dichloroethene. And down here, where they are trans to each other, we say that this is trans 1,2-dichloroethene. Okay, just to distinguish the two, because these two species could have totally different properties. Okay, totally different properties, which means that well, physical properties, but not chemical properties, of course, which means that they're different species. You know what I mean? You can't have two people who is the same unless they have split personalities, so to speak. But anyway, so that's how you get your cis-trans isomers. I'm just going to do one more example so you can get to see it very clearly what I'm talking about here. All right, so this case I'm going to actually do 2-butene. I'm doing 2-butene. So what I'm going to do first is draw 2-butene. Okay, and then attached to 2-butene, there's a hydrogen there, there's a hydrogen there, there's a CH3 there, there's a CH3 there. Now, some of you are saying, oh, that's not 2-butene, that's 1,2-dimethyl ethene. Oh, but no, these are not branches, as you thought. These are actually a part of the chain, because I can take my pencil and draw a line from this carbon to this carbon, and that line passes through all carbons without having me to go back to get to another carbon. Okay, so I can take my pencil like this and draw my line right across, and that line passes through all carbons. So this is actually butene, and it's 2-butene. So there is 2-butene, and then I could draw another 2-butene which looks like this. Okay, so there you have it now. You have your two 2-butenes. That sounds weird. So you have your, and then now what you do is you look for the similar groups. You have the 2 CH3 groups there. Are they on the same side? Yes, they are on the same side. So that's cis 2-butene. You see what I mean? Cis 2-butene. Okay, that's supposed to be butene. And then now over here, they're trans to each other. They're diagonal. So this is going to be trans 2-butene. And that's it. That's it, really. Okay, now if you are given an example that you're supposed to draw, and your examiner, chances are will not ask you for anything too complex, okay, because they just want to know that you understand the concept of the cis-trans isomers. So if it is that you're given anything, just remember you just need to isolate your double bond, and then you find the similar groups attached to that double bond. Okay, and of course, once you have done that, you can draw them with the same side, cis, or diagonal to each other, trans, and you give the species its name. Okay, so that is it, folks, for your isomers. I hope you understand it. I hope you have been learning. I hope you have been getting it. Okay, you can leave me a comment. Is there something you want me to clarify for you? Is there something you didn't understand? Leave a comment. Remember to like the video, give the video a thumbs up. Subscribe to my channel, G Squared Academy, where excellence is epitomized. Share the video with your friends. You know, lots of people are doing chemistry now. They need a little bit of extra help. Just share the video with them. It may help them understand what they're doing. So thank you guys for watching, and I'll see you next time. All the best.